problem solving session, leftover problems from last week. These are both in Teams I had shared and also in Blackboard. You can find them, I guess. Can you find them in Blackboard? Maybe not in the Blackboard, but just let me know if you do not have an access to the problems. We had solved the problem 4 already, right? And solved problem 4 in that handout already. Now let's solve problem 1. Okay. It says the volumetric heat generation in a hollow aluminum sphere of inner and outer radii of 20 centimeter and 50 centimeter respectively is given by, so you have an aluminum sphere, so you need to make sure you understand what geometric shape it is. You should be really careful. So this is a sphere, and let's say this is R1, this is R2, and R1 is given as 20 centimeters, which is 0.2 meters, and R2 is 50 centimeters, which is half a meter. And it's a hollow aluminum sphere. So my material is here. Okay. And the middle, like the inner section, is empty. And the heat generation rates are, the volumetric heat generation rate R is equal to 4.5 times 10 to 4, 1 plus 0.6 R squared. Okay. In which fancy R is in watt per meter cube, and R is in meters, the radial coordinate in meters. The inner surface of the sphere is subject to a uniform heat flux of, so let's call it Q1. Q1 is equal to 15,000 watt per meter squared. Okay. While heat is dissipated by convection to an ambient air at 25 degrees. Through the outer surface with an average heat transfer coefficient of 150 watt per meter square Kelvin. Determine the temperature of the outer surface under steady state conditions. Now, here's an important part of this problem. Now, you don't know what's happening inside, right? So it's like a black box to you. It's a hollow. You don't know what's happening. But just to give you a clue, you're given the heat flux there. You are given actually one boundary condition, which happens at R is equal to R1. Okay? And maybe you can actually supply it using some heaters. Maybe there is some, I don't know like the mechanism, but maybe there is a heater here which actually supplies that much heat. But there must be something to supply that. If there is nothing, or for example, if there is any other material which there is no heat generation in it, then there would not be anything coming into that surface. Okay, that's pretty important. For example, if you have like two spheres, 1, 2, right? And this is layer 1, this is the second layer, for example. Then if you take your system as your like material A, material B, if your system is material A, you're going to see that in minus out is plus generation is accumulation, and then if it's at steady state, and if there's no generation in A, for example, and that means if there's nothing coming in, there's nothing coming out. So that means that there's no flux at the boundary. So that would be a different situation. Okay. But here you are given some sort of flux. So it's basically maybe you put a battery there to provide that flux along with some resistances and so on. So we don't know about what's happening, but there is this flux given. Okay. Now we're going to do shell balance to find out the governing differential equations in the aluminum part. Okay. And we're going to start with the in minus out plus generation is equal to accumulation. It says in the problem, find the steady state temperature profile, right? So, sorry, find the steady state temperature of the outer surface. So the conditions are steady state. There is generation, it's given. There is in and out. So let's call the in as QR at R, and the out as QR at R plus delta R. So QR times the area, unlike the cylindrical geometry, we have 4 pi R square as the surface area of the shell, calculated at R, minus the out is QR 4 pi R squared at R plus delta R, plus the generation is volumetrically, it's the fancy R dot, times the volume of the shell is the thickness of the shell, which is delta R, times the surface area of the shell, 4 pi R squared. That's equal to 0. Then you do the simplifications, divide by 4 pi, divide by delta R, and then what you get is basically, and take the limit as delta R goes to 0, we get negative d over dr, R squared QR, plus fancy R dot, R squared is equal to 0. From here, d over dr, R squared QR is equal to negative fancy R dot, R squared. Okay. And then, oh, sorry, that's plus. Yep. Now you take the integral of this sides, right? You multiply everything by dr, like multiply both sides by dr to get d R squared QR is equal to fancy R dot R squared dr. Take the integral, and then you get R squared QR is equal to fancy R dot R cube over 3 plus some constant. You basically have like one constant here, one constant here, but if you subtract the 2, you get another constant. So let's call it just C, okay, to make it simple. And you solve for QR is equal to fancy R dot over 3 R plus C over R squared. correct? Okay, that's the flux as a function of R, but we need to write down the Fourier's law to find the temperature as a function of R, correct? Minus K I did a mistake here. R dot is given and it's not constant, and nobody's telling me that. R dot is given and it's not constant. Yeah. Okay, what is R dot? Let's see. Fancy R dot. 4.5. Ten to 4. 1 plus 0.6 R squared. Correct? dr. There you go. Plus C. So R squared QR, you get 4.5 times 10 to 4. The derivative of 1 times dr is R, plus the derivative of 0.6 times R squared is 0.2 R cubed. Correct? Plus C.
Well, aren't you missing an R squared?
Say it again.
Are you missing an R squared?
Yeah, I'm missing an R squared. How many mistakes am I doing here? Thank you for following it. Yeah, I'm missing an R squared. So this is going to be R cubed over 3. And this is going to be R to the 5 over 5, right? There you go. Yep. And I have C there. I have one boundary condition to find the C before you write down Fourier's law if you need. And the boundary condition is at R is equal to R1, which is equal to 0.2 meters, correct? I know that the flux is this much. QR is equal to Q1, which tells us that if you plug it in this equation, 0.2 meters squared times Q1 is 15,000 watt per meter cube. Sorry, watt per meter squared is equal to 4.5 times 10 to 4 0.2 meters cube divided by 3 plus, and I know that this has the units, right? So this has the units of what? This thing should have the units of this. But the 0.6 must also have the units. It must be 1 over meter squared to make this unitless. Watt per meter cube plus 0.6 meter to the power 2 divided by 5 0.2 meters to the power 5 plus c. Let's do the algebra. I have a calculator. I recommend you to also do it because I have been doing so many mistakes these days. 0.2 squared times 15,000. 600 watts on the left hand side. Five times 6 divided by 5. Hundred and 21.7 watts plus C. So you get the C as 478.3. There you go. Did you get the same answer? Okay. Okay, so we have the R squared QR. So let's write it. R squared QR is equal to 4.5 times 10 to 4 R cubed over 3 plus 0.6 over 5 R to the 5 plus 478.3. Now, I could have written the Fourier's law right now and do another integration and get another constant and do all these things, but I guess I don't need it because you know what? The other boundary condition, it doesn't tell me anything about the surface temperature. So it's not going to be probably useful because it's asking the outer surface temperature. So we don't know it. So it's going to be really difficult for me to find out any constant popping out after taking another integration by writing the Fourier's law. Instead, I can just write the heat lost from the outside surface, and I can equate it to the Newton's law of cooling, to the temperature differences, and it's going to give me directly the temperature itself. So the plan is find the heat lost through the outermost surface and use Newton's law of cooling to find temperature differences, T surface minus T infinity, and thus T surface. Okay, so that's the plan. So what is the heat loss through the outermost surface? Q lost to the surrounding. It's basically the flux at the outer surface, right? It's the surface area 4 pi R squared R2 squared times QR at R2, right? That must be equal to H times area 4 pi R2, 4 pi R2 squared times the temperature difference, Ts minus T infinity. And I'm assuming that it's losing heat, so that's why I wrote it Ts minus T infinity to make it positive. Ts is larger than T infinity. Okay, so I can actually use this equation and simplify this thing. 4 pi's cancel, right? And then R2 squared QR at R2 is equal to H times R2 squared Ts minus T infinity. And this left-hand side is nothing but the R squared QR estimated at R2, right? So you know it actually from here, if you realize. So I can calculate it at R2. It's equal to H times R2 squared Ts minus T infinity. Let me plug in all the numbers and let me actually make use of this thing to get 4.5 times 10 to 4. R2 is 0.5 meters, so I'm going to plug in 0.5 cubed divided by 3. Let's forget about the units for the time being. Plus 0.6 divided by 5. 0.5 to 5 plus 478.3 is equal to the right-hand side now. H was given 150. And you make sure it's the SI units. Yeah, it's given in SI units. Times the R2 squared. 0.5 squared. Ts is unknown, and the T infinity is 25 degrees. Good. There you go. And let's do the algebra.
Wait, do we need the 25 degrees to be in Kelvin? Because the left side's, I think, in Kelvin.
Yeah, so here's the thing. As I mentioned before, temperature differences, if you have a temperature differences of 10 centigrade, it is the same as the temperature differences in 10 Kelvin. We talked about this before, right? So for example, 300 Kelvin and 300 Kelvin is what? Or maybe let's say this. 273 Kelvin is 0 degrees, right?
Yes.
And 27 degrees is 300 Kelvin, right? But the difference between the two is the same, no matter which units you use. So that's the that's one good thing about the Kelvins and centigrade. They are actually, when you talk about the differences, they have the same units. So you can write it in Kelvin if you like, which is 298 Kelvin. But then you're going to find in Kelvin this thing. But then you can subtract that 273 to go back to centigrade. So you can write it in this form. If you write it in Kelvin, Ts you're going to find in Kelvin. If you write it in centigrade, if you write it in centigrade, though, you're going to find the Ts in centigrade. Does that make sense?
Yes, thank you.
No problem. But if it were like an absolute temperature like T instead of a difference, I would not be allowed to multiply with a centigrade if it were a Kelvin. Okay? But this is a temperature difference, not the temperature itself. And the temperature differences in Fahrenheit would be completely different. Yeah, you would actually be able, you would first convert it in Fahrenheit. But for the Kelvins and centigrades, they are actually consistent with each other. Okay. You don't have a multiplication. I mean, in other words of saying that Kelvin is just something plus centigrade, or centigrade is something plus Kelvin. So you do not have a conversion factor between them. The conversion factor is 1, but you just shift it. Okay, so let's do the left-hand side. Got 2, 5, 2, 2 on the left-hand side. Yeah, so I got TS is equal to 92.3 centigrade, not Kelvin. Okay. Any questions so far? So that's the answer for the first problem. If you don't have any questions, let's solve problem number 2. Okay. Cylindrical stainless steel containers with inner and outer diameters of 1 meter and 1.2 meter respectively are used to store radioactive waste underwater at 25 degrees. So let me draw the schematics. This is RI, and this is R's, R out. This is T out. This is T in. And here you have the radioactive waste. Okay, this is water at 25 degrees centigrade. This is H. It's given 1,000 watt per meter squared Kelvin. Okay, and RI is given 0.5 meters, and R out is given 0.6 meters. Okay. So what's being asked? That's very important, because whatever is being asked might actually change how we are going to solve the problem. So it says calculate the inner and outer surface temperatures of the stainless steel casing under steady state conditions. So the question is asking what is TI and what is T out. Okay. Okay. Thermal conductivity is given. K. Thermal conductivity of the steel, 15 divided by meter Kelvin. 15 watts divided by meter Kelvin. and waste generates heat at a volumetric rate of 2 times 10 to 5 watt per meter cube. Okay, so that's it. Okay, so let's calculate the in and out temperature. So what are we going to do? We're going to do a shell balance, right? We're going to pick a shell. Q in, Q out. Okay, QR at R, QR at R plus delta R. We say in minus out plus generation is equal to accumulation, correct? And do I have any accumulation? No. Do I have any generation within the shell? Yes or no? What do you think?
No.
No, we don't. Excellent. We don't have any generation within my shell because that's the system that I pick. If I had picked my system as my radioactive waste here, yes, there would be generation. But now there is no generation within the steel material. So generation is 0. And the in is the flux times the area. Now this is a cylindrical geometry, right? This is a cylindrical shell. So the surface area of the cylinder is 2 pi r, the circumference of this circle, times the L, the length. It's like the area of a folded, not folded, but rolled paper. Yeah, the area of a rolled paper, 2 pi RL. It's at R minus what's going out is the same quantity, but estimated at R plus delta R. Is equal to 0. Now, from here, you can get rid of the 2 pi's if you like. You can divide by 2 pi, and also L, maybe. Those are constants, right? And what you find is basically, and you divide by delta R, both sides. What you get is actually negative d over dr r qr is equal to 0 after you take the limits delta R goes to 0. And this says that R times QR is constant. Okay. Well, here you can say, okay, R times QR constant, but let me actually convert it in a much useful quantity. It's an optional thing. You don't need to do it, but I like to multiply this thing with the 2 pi L. Again, I want to actually get, I don't want to get rid of these things, and I want to get them back. So it's going to be something like 2 pi RL QR is going to be another constant. So it's going to be 2 pi times L constant. Let me call it C1. Okay. And the boundary condition that you can actually use before actually moving to the temperature profile, I think it's a good idea to write down the flux at this surface, at this inner surface. Okay. And you can say at R is equal to Ri, the flux QR at Ri is nothing but whatever is being generated within the waste, Q generation, divided by the surface area, the inner surface area, 2 pi Ri L. Okay. Is there anybody who wants to get convinced about this statement? I mean, is this clear? Okay, so that's clear. I mean, you can actually come up with this by actually choosing waste, the waste material as your system, and say in minus out plus generation is accumulation, and you say that no accumulation is there and there is generation. Let's say there is nothing in, but there's only something going out here, right? The waste is losing some energy. So you can say that minus out plus generation is 0. From here you find that the generation is out. So, but whatever is outputted from the waste is inputted to the steel system as a flux at that surface. That's where this term comes. Okay, that's the heat transfer to the steel at the Ri boundary. So that's this is a nice way of thinking about it. So that explains the boundary condition. And you can also write it as two pi RIL QR at Ri is equal to Q generation. But the Q generation is nothing but the volumetric, uniform volumetric heat generation rate times the volume of the waste, right? And the left-hand side, this one, is nothing but this term being evaluated at Ri. 2 pi R L QR evaluated at Ri. But we know that this is a constant, so no matter where you calculate it, you're going to find that it has C1 already, right? So this term is C1 is equal to fancy R times the volume of the waste. Volume of the waste is the volume of the sphere, pi Ri squared times L. Right? Okay, there you go. So you found the C1. So from here, and using this one, we write it as 2 pi RL, 2 pi RL QR is equal to C1, which is fancy R dot pi Ri squared L. Okay, and then you do the simplifications. Pi's cancel, L's cancel. What do you get? We get QR is equal to fancy R dot Ri squared divided by 2, 1 over R. So it's some constant times 1 over R. Okay, good. So we found the flux, but we need the temperature distribution, right? Let's write the Fourier's law. So QR is nothing but negative K of the steel, del T over del R is equal to fancy R dot Ri squared over 2, 1 over R. Now let me, I know that the temperature only changes radially, so I can convert the partial derivatives to total derivatives. So I can say dt over dr is equal to negative fancy R dot Ri squared over 2k 1 over r. Now I multiply both sides by dr to get dt is equal to negative fancy r dot ri squared over 2k. Now fancy r dot is a constant number, so when I take the integral of both sides, it can come out of the integral as the other constants. So you get something like t is equal to negative fancy r dot ri squared over 2k. Integral of 1 over r is logarithm of r. Okay. Plus c, or let's call it c2. And the boundary condition we need here, at r is equal to r out, right? The flux, the QR at RO is equal to the Newton's law of cooling, H T at R out minus T infinity, right? And from here, we know that the QR at R0, QR at any R is this, so I'm just going to plug in that one. Fancy R dot Ri squared over 2R RO. It was R, but I need to replace it by RO is equal to H times the temperature estimated at RO is, we're going to plug in RO in this equation instead of R, negative fancy R dot Ri squared over 2k logarithm of RO plus C2 minus this T infinity. Okay. And then you can take this H to the denominator here and solve for C2. So C2 becomes equal to fancy R dot Ri squared over 2H RO plus fancy R dot Ri squared over 2k logarithm of RO plus T infinity. Okay. And then if you plug this in here and combine this term with this term, you get the following. T is equal to negative R dot Ri squared over 2k, okay, logarithm of R over RO, because I'm subtracting this from this because the prefactors are the same. Okay. And then I have fancy R dot Ri squared over 2H RO plus T infinity. So that's my equation for the temperature. Now you should insert the given numbers, inserting the given numbers for fancy R dot Ri, RO, H, T infinity, and K. You get the following. T is equal to negative 1,670 logarithm of r over 0.6 meters plus 66.7 degrees centigrade. And so if you plug in the Ri in here, Ti comes out to be equal to 371 degrees centigrade. You plug in R is equal to Ri, you get this. And then if you plug in R is equal to R out, you get T out is equal to 66.7 degrees centigrade. Okay, so that's the solution. Now, it looks like a pretty long way of solving it, right? But you can come up with a shorter way, a second method if you like. I can show it to you. Do you want me to show you another method, a shorter method, or you're fine with this?
I can show a different method.
You wanna hear about it?
Yes.
Okay, sure. An alternative method. So let's say this is method 1. Long solution. Method 2. Shorter way. So you need to first appreciate the fact that the Q is constant throughout the radial direction. You should make this observation first. The reason is because within the steel, by the way, within the steel, although the flux is not constant, the heat transfer rate is constant. It changes per unit area, but it doesn't change as a total, like joules per second. The reason is because if you do the shell balance in the steel, right? If you had realized, you can say, okay, Q in, Q out. Well, basically Q in minus Q out plus 0 is equal to 0. So Q in is equal to Q out. Basically, although the flux changes just because the area changes, the Q in is equal to Q out. So basically, Q doesn't change along the steel. So you can actually, you don't need to make even get even a small shell. So you should get, for example, if this is your steel, you can take your entire steel as your system, even if you think so. If you can take something like a thicker shell, right? Whatever is going like Q in is gonna go Q out. So Q in is gonna be equal to Q out. So Q is constant throughout the radial direction. That's one thing you should appreciate. Then once you actually realize that, you can say that, okay, that Q is equal to, must be equal to whatever is being generated within the waste, right? As we actually said here, this entire generation in this waste should be actually released to the steel, and the Q within the steel must be equal to that total amount of generation per unit time. And it's basically nothing but the volumetric generation rate times the volume of the waste, which is pi Ri squared L, right? And you can say that that Q transferred within a spherical shell, right? That Q transported within a spherical shell. We know from our earlier analysis about the overall heat transfer coefficients, right? We said that it's the temperature differences, Ti minus T out, divided by the resistance. And we had derived it earlier that the resistance for a cylindrical shell, is nothing but logarithm of Rho over Ri divided by 2 pi Lk, right? And that's also equal to whatever is being lost from the outside, which is equal to H times the area, which is 2 pi R out L times T out minus T infinity. Okay. And the first thing you can do is you can make use of, first, you have two equations here. You can make use of this equation first, and then you can use this equation. So if you use, for example, this equation, then the only unknown is T out. So you can actually find out the T out from here. Okay. And it gives you the following. Fancy R dot pi Ri squared L is equal to 2 pi R out L H T O minus T infinity. Pi's and L's cancel. Fancy R Ri squared divided by 2 Rho H is equal to T O minus T infinity. From here, you solve for T out, which is T infinity plus fancy R dot Ri squared over 2 Rho H. And if you plug in the numbers, you would find that after plugging in the numbers, you get T out is equal to 66.7 degrees centigrade. And then once you know the T out, then you can use this equation to solve for the Ti. So you say that Ti minus T out divided by logarithm of R out divided by Ri divided by 2 pi Lk is equal to fancy R dot pi Ri squared L. Okay. And then you make this upside down to make it look like Ti minus T out 2 pi Lk over logarithm of Rho over Ri is equal to fancy R dot pi Ri squared L, right? And the pi's and L's cancel again. Oops. And you solve for Ti. Ti comes out to be T out plus fancy R dot Ri squared logarithm of Rho over Ri divided by 2k. And if you plug in the numbers, we get Ti is equal to 370.6 degrees centigrade. That solves the problem, and it's the second method. Although they look exactly the same length, I wrote largely here, but I think this is a much simpler way. But you should actually know, or maybe make use of the formula that we already had found out earlier.